Have you ever, like, looked at your calendar on a Monday morning and promised yourself, or maybe your boss, that you were going to finish 5 major projects by Friday?
Oh, yeah, constantly.
Right. And then you get to Thursday afternoon and suddenly realize, well, there's still only 24 hours in a day.
It is just a brutal realization. I mean, you're staring down the barrel of a completely fixed resource, time. And you just have to recognize that your ambition massively outpaced your reality.
Yeah, you run out of time, you scramble, maybe you burn the midnight oil, or worse, you just have to tell someone you aren't going to deliver on time.
Which is the worst feeling.
Exactly. And in the business world, that scenario is what we call a fundamental capacity failure. So today, we are mastering something called capacity requirements planning, or CRP.
It's a huge topic.
It is. We are taking a massive stack of training materials from APDS, which, is basically the gold standard association for supply chain management. And we're extracting the ultimate shortcut to understanding how professionals balance time, load, and reality, and how they do it without completely burning out.
Because it's one thing to mismanage your personal calendar, right? It is an entirely different level of catastrophe to mismanage the schedule of a factory floor.
Oh, for sure.
I mean, you've got hundreds of heavy machines, thousands of workers, millions of dollars in raw materials just moving around. You need a highly rigorous system to keep all of that from collapsing.
Okay, let's unpack this by actually starting as far away from a factory floor as possible. Because before we get into the heavy math of manufacturing, we need to understand capacity in its most rigid, unforgiving environment.
Right.
And according to our sources, that isn't a steel mill. It is the service industry.
That is the perfect baseline. When we talk about services, so hotels, restaurants, airlines, we are dealing with a type of capacity that is subject to intense scarcity.
It's just hard to get.
Exactly. It's incredibly expensive to build out. And once you actually have it, well, it significantly increases your financial break-even point. But the absolute most critical concept to grasp here is that services are inherently perishable.
Perishable. Okay, when I hear that, I immediately think of, like, a carton of milk going sour or bananas going bad on the kitchen counter.
It's a similar concept for sure, but the timeline is far more strict. The sources actually highlight the hotel industry to illustrate this. Think about a physical hotel room. It has a shelf life of exactly 1 day.
Right.
If that room is not booked for a Tuesday night, the capacity of that room and obviously the potential revenue it represents is just gone forever.
You can't box it up.
No, you cannot sell Tuesday's empty room on a Wednesday. The time has just evaporated.
I see. It reminds me of an empty seat on a commercial airplane taking off.
Yes, great example.
Like, once those wheels leave the tarmac, you can never, ever sell that specific seat for that specific flight again.
Yeah.
It's just permanently lost capacity.
What's fascinating here is why tangibility matters so much. I mean, in traditional manufacturing, if you produce a physical product, let's say a coaster, and nobody buys it today, you just put it on a warehouse shelf.
Right, you just store it.
Exactly. That physical inventory absorbs the shock of fluctuating customer demand. But in the service industry, your inventory is just raw time.
Wow. Raw time.
Yeah. That means demand and capacity have to align perfectly in real time, or you just lose the value completely.
So if you're a service manager and you can't just put your extra time in a warehouse for later, how do you adjust when, say, a sudden rush of customers comes in or when nobody shows up at all?
Well, you have to pull very specific operational levers. You might change your workforce levels by hiring seasonal help.
Okay.
Or you can cross-train your staff. So maybe the front desk clerk can suddenly jump in and help out the restaurant if it gets swamped.
Oh, that makes sense.
You might increase customer participation, like installing self-checkout kiosks. You can lean into automation, or you can simply extend your hours of operation to stretch out that daily capacity container.
That sets the stakes perfectly, honestly. Time is the ultimate perishable good.
But, since you can't just store time in a warehouse, how do manufacturers manage it to ensure they don't overpromise to their customers?
They rely on a strict repeating logical loop. This is the capacity requirements planning process, the CRP.
Okay, the famous 5 steps.
Right. Instead of just hoping for the best, planners constantly calculate exactly how much available capacity they have. That's step 1, figuring out their actual muscle.
Got it.
Then step 2, they calculate the load. That's the weight of the work they need to accomplish in a specific time frame.
And I imagine they just compare the 2 numbers to see if they're about to, drop the weight.
Essentially, yes. For step 3, they generate work center load reports that visualize exactly where the stress points are on the factory floor.
like finding the bottlenecks. Exactly.
Yeah.
And then comes the critical moment, which is step 4, resolving the differences. If you have too much work and not enough capacity, you have to fix it.
Right.
But the golden rule of CRP is that you attempt to adjust your available capacity first. And then, only as an absolute last resort, do you change your priority plan to match the limited capacity you have. Finally, step 5 is just preparing that plan for execution.
Wait, hold on. I'm looking at this workflow and I really need to push back on that 4th step.
Sure, go ahead.
Why on earth would we bend over backward to adjust the capacity before simply changing the plan? I mean, if we are overloaded, if we just don't have the hours, shouldn't we just call the customer, tell them no, or maybe push the due date back a week? Wouldn't authorizing massive amounts of factory overtime just completely crush our profit margins?
It is a highly counterintuitive rule for a lot of people outside of operations. I get it. To understand it, you have to realize what that priority plan actually represents. In a supply chain, the priority plan is typically your master production schedule, the MPS, which dictates exactly what you are building and when, and your material requirements planning, the MRP, which orders all the raw materials needed to build it.
So it is basically the central nervous system of the entire operation.
If we connect this to the bigger picture, the priority plan is the engine driving everything. If you just casually push a due date back a week, you aren't just annoying one customer.
What else happens?
You are triggering a massive destructive cascade. You have to call 50 different vendors to delay parts shipments. Your purchasing managers are thrown into chaos. Trucks are arriving with raw materials that now have literally nowhere to be stored.
Oh, wow. I didn't think about the trucks.
Yeah, and workers scheduled for downstream assembly lines are suddenly just standing around idle.
Ah, I see. The ripple effect of dismantling the plan is far more expensive than just dealing with the bottleneck locally.
Radically more expensive. It is almost always cheaper in the long run to try and stretch your capacity. By authorizing time and a half for a weekend shift or outsourcing a small subassembly to a third party rather than dismantling the entire master production schedule. In supply chain management, moving the goalposts is always the final act of desperation.
Okay, you protect the master schedule at all costs, I'm convinced. But to even know if we are in trouble, we have to calculate our capacity accurately in the first place.
Right, which goes back to step 1.
Yeah, and looking at the sources, figuring out how many hours a factory has, isn't as simple as just looking at a clock on the wall.
Far from it. 8 hours on a clock rarely translates into 8 hours of actual productive work. We have to calculate the crucial difference between theoretical potential and proven, gritty reality.
Right. To do this, the materials introduce standard time, or standard hours, as the common unit of measure. And standard time is definitely not just the time a machine is actively spinning.
No, it encompasses the entire reality of the task. Standard time includes the set-up time required to prep a machine, like cleaning out the grease from a previous run or recalibrating cutting lasers.
All right.
It includes the actual run time, but most importantly, it accounts for scheduled rest for an average worker and unavoidable delays.
Give me a real-world example of an unavoidable delay. Like, what are we actually factoring in here?
Think about the physical realities of a heavy industrial environment. An unavoidable delay could be a union-mandated 15-minute break every 4 hours.
Oh, right. You have to account for that.
Yeah, or it could be the fact that a massive industrial furnace takes 45 minutes just to reach operating temperature before you can even put a single part inside it.
Yeah, or maybe the time it takes a forklift driver to clear away a bin of sharp scrap metal so the operator can safely stand at their station.
Exactly. Standard time bakes all of that friction into the metric.
So what does this all mean? We have a baseline of what should happen under normal conditions, with all that friction accounted for. How do we actually measure our team against that standard?
We calculate efficiency. The formula is standard hours produced divided by actual hours worked.
Let's ground this with a really simple analogy before we get into the heavy factory math.
I love a good analogy.
Say I am baking batches of cookies, and the standard time to prep and bake one batch is 20 minutes. But I am highly motivated, and I managed to crank out 3 batches.
Okay.
So 3 batches times 20 minutes each equals 60 minutes of standard work accomplished. But let's say I did all of that in just 45 actual minutes.
In that scenario, you take the 60 standard minutes you produced divided by the 45 actual minutes you worked, and you get an efficiency of 1.33, or 133%.
Nice.
You are operating well above the expected baseline. You are a highly efficient baker.
I'll take that compliment.
Yeah.
But efficiency is really only half the story in a factory, right?
Right. The other critical metric is utilization. Utilization is the actual hours worked divided by the available time.
Why is that different?
Because think about a robotic welding arm. It might be incredibly fast and efficient when it is actually welding, but if it is broken down or waiting on parts or sitting idle for half the shift, its utilization is terrible. You are paying for capacity you aren't using.
Which brings us to the grand formula for rated capacity. Rated capacity equals available time multiplied by utilization multiplied by efficiency.
Exactly.
And the AP cell source gives a fantastic scaled-up example of this. Imagine a factory work center has 240 hours of available time in a given week. Through observation, they know they have a utilization rate of 95% or 0.95 and an efficiency rate of 103% or 1.03.
So you run the calculation. The 240 available hours multiplied by 0.95 utilization multiplied by 1.03 efficiency.
Let me just think through that math.
The result is 234.84 standard hours. That specific number is your rated capacity. It is the math nerd prediction of exactly how much work that center can handle this week.
But then the materials introduce a competing concept, which is demonstrated capacity. I mean, we have a solid math equation for rated capacity, so why do we need this other metric?
Because demonstrated capacity is your proven historical reality. It strips away the theoretical formulas. You find it by simply looking at the historical output of a work center and averaging it over time.
Just a straight average.
Yep. And it is crucial to note, it is an average, not the absolute maximum output they ever achieved on their best day.
The source is actually given an example of looking at the last 4 weeks of a production line. If that line produced 100, 110, 90, and 120 standard hours over 4 consecutive weeks, you just average those 4 numbers together.
Right.
The result is 105 standard hours. That is your demonstrated capacity. It already has all those utilization and efficiency quirks baked into it organically.
Precisely. Because it is based entirely on what actually happened, not what a spreadsheet said should happen. It is the ultimate reality check.
That makes a lot of sense.
And what is fascinating about this dynamic is that demonstrated capacity requires historical data. If you are launching a brand new product on a completely redesigned assembly line, you don't have any history to average.
Oh, right. You're flying blind.
That is exactly why supply chain professionals need those rated capacity formulas. You use rated capacity to predict the future for new lines, and you use demonstrated capacity to verify the gritty reality of existing ones.
Okay, so we know the exact size of the container. We know how much time we have. Now we have to figure out the volume of the liquid we're pouring into it. We need to measure the load to see if it actually fits.
Calculating the load is a fairly straightforward equation. For any given order, the operation time is the setup time plus the quantity of items multiplied by the standard time per unit.
Okay.
You run that math for every single order scheduled to pass through that work center, add it all together, and you have your total load.
But, I mean, knowing how much work we have is useless unless we know exactly when to do it. The materials dive deeply into production activity control, or PAC, and this concept of backscheduling. Explain how this works, because it entirely flips how most people naturally think about organizing their day.
Yeah, most people naturally default to forward scheduling. I am handed a task, I start it today, I work until I'm done, and I see when I finish.
Right.
Backscheduling works completely in reverse. Production activity control looks at the final, non-negotiable due date of the customer order and works backward in time to determine the exact finish and start dates for every single operation in the sequence.
The inputs for this simulation are pretty intense. They use the quantity, the due date, the operation time we just calculated, and the routing sequence.
Yeah, meaning it has to go to the cutting machine first, then the sander, then the paint booth.
Right. But crucially, they also factor in queue time, which is the time parts spend just waiting in line to be worked on. Wait time, which is waiting after the work is done. And move time, which is literally the physical transit time, moving heavy parts across a massive warehouse.
And the rule of thumb here is to round up to the nearest whole day for these buffers just to be safe. It creates a highly precise, highly orchestrated timeline.
Here's where it gets really interesting, because as I was reading this, I realized I actually use complex back scheduling in my real life. It's exactly the logic you use to plan a massive Thanksgiving dinner.
Oh, like this translation. Walk us through the Thanksgiving schedule.
Okay, so you don't just wake up on Thanksgiving morning and randomly start turning on ovens and chopping vegetables whenever you feel like it.
No, definitely not.
That is forward scheduling, and if you do that, you'll end up eating dry turkey at midnight. With Thanksgiving, you start with the rigid due date. We sit down at the dining table to eat at exactly 5:00 p.m. That is your master production schedule. Then you work backward. The turkey needs 30 minutes of resting time. That's your wait time. It needs 4 hours to roast. That's run time. It needs 20 minutes to prep and season. That's setup time.
Right.
So you calculate backward from 5:00 p.m. to figure out exactly when that bird needs to go into the oven. And you map those routings for the potatoes, the stuffing, the pie, so they all hit the table hot at precisely 5:00 p.m.
That is a brilliant analogy. And if we look at the core business reason factories use backscheduling, it is explicitly designed for environments where maintaining low inventory is a top priority.
Like keeping the food hot.
Exactly. Just like you don't want your Thanksgiving turkey sitting on the kitchen counter getting cold for 3 hours while the potatoes finish, a factory manager doesn't want thousands of finished carburetors just sitting around collecting dust.
Because that takes up expensive warehouse space.
Yeah, and it ties up the company's operating capital. Backscheduling ensures that production is perfectly synchronized with the exact moment the customer needs the order to ship out the door.
Okay, so we've calculated our capacity, we've scheduled our load beautifully, and we are ready for Thanksgiving dinner. But let's face the harsh reality of the factory floor. The math doesn't always work out perfectly.
It rarely does.
Right. What happens when you simulate the schedule and you realize you have 150 hours of work scheduled in a work center that only has 105 hours of demonstrated capacity? The turkey and the green bean casserole both require an oven at 350 degrees at the exact same time, and you only own one oven.
That is the ultimate moment of truth in capacity planning. You have identified a critical imbalance, and now you have to resolve it.
The materials detail a specific toolkit for plant managers facing this crisis. You can try to redistribute the load, moving some of the work to an alternate work center.
Yes.
You can modify operation priorities, forcing leadership to decide which client order is truly the most urgent. You can use lot splitting, where you send half a batch to the next machine before the first half is even finished, just to keep things moving.
But the one tactic that almost always sparks a fierce debate on the factory floor is using alternate routings.
Yes, I zeroed in on that too. Using an alternate routing means taking the work away from your primary, state-of-the-art, most efficient machine and intentionally sending it to a different, likely older, slower, or less efficient machine.
Right.
My pushback here is, isn't that inherently self-defeating? Aren't we just trading a bottleneck for a bad, expensive process? Why would a manager intentionally choose to be less efficient?
This raises an important question about how we actually define efficiency. And this specific nuance separates average planners from great ones.
Okay, I'm listening.
You are absolutely right that you might lose localized efficiency at that specific alternative workstation. The older secondary machine might take 30 minutes to cut a unit instead of 20. It might require more manual labor. The cost per unit goes up slightly.
Which sounds bad.
It does. But what you gain in exchange is net system efficiency.
Net system efficiency.
Think of the factory workflow as a fast-moving river. If a dam gets blocked, which is your hopelessly overloaded primary machine, the entire river downstream dries up. Every single machine after that bottleneck is starved of work. They are sitting idle. The workers are standing around checking their watches. You are burning money. So yes, intentionally using an alternate routing might cost a little more time and money at that one specific step, but it keeps the river flowing.
I see.
It is always, always better to have a slightly slower secondary machine producing parts than to have the entire downstream supply chain starved and idle because your quote-unquote efficient primary machine couldn't handle the load.
Wow. That completely reframes the whole concept. You aren't looking at the efficiency of a single piece of metal. You are managing the efficiency of the entire factory as a single living organism. You sacrifice a little bit locally to win globally.
That is the essence of capacity management.
That is a massive takeaway. So to wrap up our deep dive today, we've covered incredible ground. We started by exploring the perishable nature of a vacant hotel room, learning that pure time is the ultimate disappearing asset.
Yeah.
We walked through the rigid math of converting a messy factory floor into standard hours, measuring both efficiency and utilization to find our true rated capacity. We planned a Thanksgiving dinner using backscheduling to ensure expensive inventory never sits around collecting dust. And finally, we learned that sometimes you have to intentionally embrace a localized inefficiency just to keep the entire system flowing smoothly.
It really highlights how much art and human psychology is mixed in with all this heavy math. Balancing capacity isn't just about plugging numbers into a spreadsheet, it's about anticipating the friction of the real world.
And speaking of anticipating the real world, I know you wanted to leave our listener with one final thought to ponder as we close out.
I do. Throughout this entire discussion, every single formula we've explored to calculate standard time has been firmly based on the extensive observation of an average human worker.
Right.
We account for human fatigue, union breaks, and physical limitations. But I want you to consider what happens to capacity requirements planning when true AI and advanced robotics fully integrate into this loop.
Oh.
If a machine learning algorithm dynamically improves its own physical runtime with every single unit it produces, constantly finding micro-efficiencies humans can't even perceive, the standard time shrinks continuously.
It never stabilizes.
Exactly. If the machine's learning curve approaches zero and robots don't need scheduled rest, does our capacity effectively become infinite? How will supply chain professionals even begin to build a master production schedule for a future where capacity recalculates itself faster and faster by the second?
That is a wild thought to leave on, trying to measure a constantly shifting baseline of reality. Thank you so much for joining us on this deep dive. Take these concepts, maybe even the Thanksgiving analogy, into your next big project planning session. We'll catch you next time.